Last lecture today, applications of the Green's function in thermoacoustics. So the previous lecture was a kind of general introduction into the Green's function and the sort of way you can use it as a building block. And in thermoacoustics, it's particularly useful, as we shall see in this talk. Right, outline is I'm basically talking about two applications. One is time history calculations, and the other is stability analysis for individual modes in a nonlinear context. And for the time history calculations, I'm going to show the Green's function method and then compare it with the Galerkin method. Okay, so time history calculations. We have our governing equation with a heat release sourcing term, a heat release term as a source term. So this is a very typical equation that we encounter in thermoacoustics. And the Q dashed in here is the fluctuation of heat release, of rate of heat release per unit mass. This is written in terms of the velocity potential phi. Sometimes you see it in a different form where the heat release has a time derivative. And this is the form where the variable, the field that is considered, is the pressure rather than the velocity potential. But the structure of the equation is very much the same. We have the wave equation term on the left and then a forcing term involving the rate of heat release on the right. So we have a forced partial differential equation, and that's just an ideal candidate for a Green's function approach, which we know has this governing equation in the one-dimensional case. This can be combined with the equation for phi, as we've seen in the earlier lecture. The only difference is that now I've got a specific source term, which is due to a heat release rate in there, rather than the general source term that I denoted by S. And if you combine these two equations, after a number of manipulations, you get this integral equation, which we've seen a number of times before. Here we have the heat release rate term, and for a compact heat source, we can write the heat release term in terms of a delta function in x, simplify the integral, and only have one integral over the source time, which is this equation. Now I'm going to manipulate this equation to make it useful for our purposes. So what I'm going to do is I'm going to differentiate both sides with respect to x. So instead of phi, we get from phi we get d phi by dx, and the x derivative also acts on the g, so we get a dg by dx. And then I'm going to evaluate the equation at the observer point xq. That's why there are these x equals xq here. So what this gives is an equation for the velocity, because d phi by dx is the velocity in the one-dimensional case. I've denoted that by uq, q for source, that's the velocity at the heat source. Then this constant is just the same, the integral is just the same, and then the derivative acts on this Green's function, which we see here, and then we have the heat release rate and the dt star. Now, to take this further, we need to know how this q, how the heat release rate is related to the velocity. And for our purposes, we assume that we have a time lag law. So it's q depends on the velocity at the heat source, but at an earlier time, and tau is the time lag. The exact form of this functional dependence is not important for our purposes. It can be a linear relationship, it can be a nonlinear relationship, anything is possible. Okay, so what we get when we insert for this q of t, if we insert our heat release characteristic, is this integral equation, which has become two-colored. On the left we have the velocity at the current time t. The current time t also appears in the upper integration limit, and then in the integral we have the velocities, but at earlier times. The sort of biggest time is t, so the highest time is t minus tau, which is still earlier than this velocity. So we have related the velocity at the current time to the velocity at earlier times, and the Green's function we know. Basically what we've got here is an integral equation for the velocity, for the uq. And it's a particular type of integral equation. It's a Volterra integral equation, which is the fact that we have an upper limit in the integral which depends on this variable makes it the Volterra integral equation, but that's just a name. Right, and yeah, this can be solved with a time-stepping method, and I want to illustrate that on the next slide. So we're going to discretize the observer time. We start with a t0, then delta t, where delta t is a small time interval, 2 delta t up to generally m delta t. Same for the source time, t star j is j times delta t. The integral, when discretized, becomes a sum. And then our integral equation becomes this equation, which involves this sum. So we have the uq at our discrete times tm, the heat release rate, which we know depends on u, and then here I've introduced an abbreviation because this x derivative of the Green's function is rather messy. So just to make things a bit more compact, make the equation more compact, I've introduced this abbreviation. But just read Green's function for that. Just it's a very close relative of the Green's function. And this equation can be solved iteratively. So when you do an iteration, you need to start somewhere. So you need initial conditions, and here we need to assume that we know the initial heat pulse. So q at time 0 is some given q naught, and we also assume that the velocity before t equals 0 is 0. So this time lag velocity is 0 before t minus 2 before when this inequality is satisfied. Right, so let's write down what we get explicitly in the first few iteration steps. So let's take the first iteration step, that's m equals 0 and tm equals 0. Then we have our initial condition, q naught is equal to, q at naught is equal to q naught. And our uq, well, we have just one term in the sum, in that sum here. That's for m equals 0, and that's the term g at naught and q at naught. So that's what we have here. Then let's move on a time step. Let's go to m equals 1. Our tm becomes delta t. The q at delta t we get from the heat release characteristic. We know this velocity from the initial conditions. And then our integral equation gives us, or sum rather, this sum now has two terms in it, and those two terms are given here and here. And you can see that as you go up, as you sort of go further and further into the iteration, you get more and more terms. With every new time step, you get an extra term to add. And all these terms have to be calculated afresh, these individual terms. I mean, this term doesn't appear earlier in the iteration, so it's numerically not a practical way of using the Green's function. So I've pointed this out here. As m increases, more and more terms need to be calculated and added. So let's find a way around that. Well, the idea here is that we know rather more about the Green's function. We know that it's a superposition of modes and that it has a time dependence which is given by the resonance frequencies. So let's use that information and try to develop a sort of cleverer iteration scheme which is numerically easier to handle. So our Green's function is a superposition of modes, and of course it's 0 before the impulse with the eigenfrequencies omega n, Green's function amplitudes gn, and then I've truncated this sum. Strictly speaking, you have to go all the way to infinity, but in practice what you have is a certain number of modes, typically the lower modes, which are important, and after about the third or fourth or fifth mode you can forget it. So the n would be whatever, depending on the actual situation, and it has a sort of easy physical interpretation. You can get it from the physics of the problem. Right, again I'm going to abbreviate this clumsy derivative to write the integral equation for uq like this, and I've now used the sum for the Green's function, the superposition of modes. Right, this, of course, the sum and the integral can be exchanged, and then we have sort of a mixture of t terms, terms with just t observer time, and then terms with the source time t star. So I'm going to sort the terms, collect all the t star terms on the right and the left, on the rest on the left, because the rest can be taken outside the integral. We are integrating with respect to source time, so this t dependence can go in front of the integral. It doesn't depend on the source time. Right, and what we get is this. That's the observer dependent time, and then here is the rest, which depends on the source time. And that is a fairly simple integral, and I'm going to abbreviate that by capital I with subscript n, and n is the mode number. Right, now let's have a closer look at this integral and see whether we can sort of develop some iteration from that. What we're going to do is we have an integration range from 0 to observer time t, and we're going to split up this integration range into two parts. One is the bulk of the integration range from 0 to t minus delta t, so just short of one time step. And then we have a remaining integral over a very short time step between t minus delta t and t. So if we write our in in terms of these two integrals, we get this. An integration from, so this integral here and this integral. If we look at the first integral, we see that it's more or less identical to our original definition of in, only at a different time, at t minus delta t. So that's the in at an earlier time, at the previous time. And this integral is an integral over a very sort of narrow integration range. And when I say narrow, I mean it's a sort of a time interval which, if you are sensible, is much smaller than the period of the highest mode. So we have a very small time interval, and we can say in that small time interval the heat release doesn't really change. We can take that some kind of average value in front of the integral, like this as q of t, and then we are left with that integral, which is the integral over an exponential function that can be evaluated, and the result you get is this. Right, so I've written down on this slide our new iteration scheme. We have our velocity given as a sum. The g's we know, the omegas we know, and the in's are the quantities that are iterated. And the iteration is sort of described by this equation. We have the previous I, and then plus this term, which can be calculated very easily. We know the q, and these are just exponential functions. And then we get the updated q from a previous velocity. And then it's on to the next iteration step. And only, as you can see, in each iteration step, you need to sum from 1 to n, so only n terms have to be calculated in each iteration step, and it doesn't blow up. So this is a much more useful way to work out the time history of the velocity through an iteration. I want to show you an example here, the example of a Ricke tube with two open ends. I've assumed that there's a hot wire goes at position xq, and for the heat release characteristic, I've used this time lag law, which is non-linear. In fact, this is the heat release characteristic from hot wire for a hot wire that's used for hot wire theory. So that's a sort of good enough first candidate for a heat release law. A and B are just constants, and in there, under that square root term, we have the magnitude of the total velocity. The u bar is the mean flow velocity, and the uq is the oscillating part of the velocity at the heat source and time lag. So you can see this is definitely nonlinear, and you should expect to see nonlinear effects kicking in when the acoustic velocity becomes close to the mean velocity. And the picture that you get from the iteration that I've just described is this. That's the time history of the velocity. Here we have time, and here we have the velocity at the heat source. And here we have an exponential increase of our acoustic velocity, which goes on until about here. At this point, we reach a velocity amplitude, acoustic velocity amplitude, which is equal to the mean flow. So this is where we start getting flow reversal, and then in all subsequent cycles, we get flow reversal for a part of the cycle. And at that stage, the sort of exponential growth breaks down. What does not happen is it doesn't give a limit cycle. So it's a smaller growth, it's no longer exponential, but it keeps growing. So this very simple heat release law that I've plugged into the iteration is, dodgy, it doesn't work. But the method should work. So if you have a decent heat release law, the method should work. Yeah, on this slide I've also plotted the corresponding the time history of the corresponding heat release rate. Here you see the initial condition. That sort of spike is the initial heat pulse that we had in the initial condition, and then again we have an exponential growth up to the flow reversal, and then after the flow reversal you sort of get something else. Right, let's summarize what we've seen so far. If we know the Taylor-Green's function and the heat release law of a thermoacoustic system, then we can calculate the time histories, not only for the acoustic velocity, but also for the rate of heat release. And the calculation method is a very straightforward iteration scheme where we step forward in time and have a fairly sort of manageable number of terms to calculate in every iteration step. Right, let's now compare this with the Galerkin method. I'll outline quickly what the Galerkin method is and how it works. The idea behind the Galerkin method is to expand the acoustic field in terms of eigenmodes, but not the exact eigenmodes of your resonator, but approximate eigenmodes. For an example, let's use a tube with open ends, and then you can write the pressure for a tube with open ends can be written in terms of these modes, which are sinusoidal. The sine gives you 0 at the boundaries, and for the velocity we have a cosine here to give you a maximum or minimum at the boundaries. So for an ideal tube with ideal open ends, this is an accurate expansion. For a non-ideal tube, it depends how sort of different it is from your end. This is hopefully an approximate representation, but it may not be. And the equations I've given here are normalized, so the omega n is just n pi. So I've normalized, instead of x, I use the variable x over L. So the integration is from x equals 0 to 1. Right. So this is, as I've said, for the ideal tube with ideal open ends, but in practice, this is a very rare scenario. In practice, tubes have an end correction. They're a bit longer than, effectively a bit longer than they are physically. In practice, you often get a temperature gradient that will change your frequencies, your resonance frequencies. You may have a change in cross-sectional area that will change your resonance frequencies. So in practice, this is dodgy. But let's sort of go ahead with it regardless. It does work, it has been used, and it has been used successfully in some cases, so I don't want to shoot it down. But I just want to point out that the Galerkin modes are an approximation to the modes, in contrast to the Green's function approach, where you have the actual physical modes in the equations. And to solve this, you base it on the conservation equations for mass and momentum. This is the equation for mass. Substitute in the modal expansion for P and U that we've seen on the previous slide, which gives this expression. And that expression, as you can see, has got this sort of sum over all the modes. They're all sort of on the left-hand side, sort of mixed up together. On the right-hand side, we just have a term that doesn't depend on n. So this looks rather messy, but there's a particular property that the sine has. It's called orthogonality. I'll say a little bit about that in a moment. Making use of the orthogonality of the sine functions, we can actually get rid of this sum and get an equation for just mode n. So this is, I hope you can read this. This is an equation relating the pressure amplitude of mode n p dot to the velocity, not amplitude, velocity of mode n un. Right, and for the momentum equation, it's a similar story. That's the equation. Substitute in the Galerkin expansions, use the orthogonality of the cosine here, and then you can separate out all the modes into an equation just for a single mode. Right, and this is just a little aside to show how this orthogonality works. It's a bit of mathematics, but it's very essential mathematics because it just makes life so much easier and doable. So orthogonality of eigenfunctions means that your eigenfunctions belong to a sort of finite system. And what you do is you take the eigenfunction for one mode, multiply it with the eigenfunction for another mode, and then integrate over the length of your system. In this case, it's a cube of length 1. And this integral is 0 if the two mode numbers n and n dashed are different. And only in the case where they are the same do you get a non-zero result, a half. And it's the same story for the cosine. Anyway, this property, which is called orthogonality, helps with separating out the modes, and I'll show that here for the mass equation. So this is the full equation with the modes all mixed in on the left. And what you do is you multiply both sides by another sign, by another eigenfunction, the one for mode n dash. So multiply the left and the right by sine n dash pi x. Then integrate over the length of the tube, and then you get this massive equation here, which continues here. Right, that seems to have made matters worse, but we have orthogonality, which tells us that this integral with respect to x, that is 0 in most cases. The only case where it's non-zero is when n and n dash coincide. So there's only one term left of that sum, that's the term n dashed. The rest is gone, so only the term n equals n dashed remains, and the equation that results is this one. So that was a quick excursion to orthogonality to illustrate how it helps to separate out the modes. Right, back to our conservation equations. So we have the equations for the velocity and pressure modes. This one is from the momentum, this is from the mass equation. They can be written in matrix form if you construct a vector like this. So the first two modes, velocity of mode 1, pressure of mode 1, then velocity of mode 2, pressure of mode 2, etc. If you construct a vector like that, you can write this equation as a matrix equation. So on the left you have these time derivative terms that come from these time derivatives. This vector with that matrix comes from these two terms, and then this term comes from the heat release term. So that's just a way of writing these two equations in matrix form, which is very compact and like this. So this is a matrix differential equation for the velocities and pressures of the individual modes. And that can be solved numerically. I've done just to illustrate it, I've done a very crude time-stepping approach by discretizing the time derivative like this. And then the resulting equation for psi, for this matrix equation, can be written like this. You can iterate on it. And for Q, you use the heat release law with the expansion for the velocity. So that can be solved iteratively. You also need initial conditions. You need to know the initial heat pulse. You need to know the initial amplitudes, un and pn, or rather, it's easiest to assume that they're just 0. And then you can perform the iteration and produce plots, time histories, just like I did with the Green's function method. And in this slide, I want to sort of compare the two methods, contrast the two methods, the Green's function method with the Galerkin method. They have a lot in common. Both methods apply to a compact heat source. They lead to explicit iteration schemes stepping forward in time, and so that means they work both for linear and nonlinear heat release laws. That's what they have in common. The differences are that with the Green's function approach, we involve real physical modes with the resonance frequencies of the system, the omega n's, and the spatial distribution of the modal amplitude, which is also an accurate physical representation. So when we truncate this sum, which goes all the way to infinity, it's very easy to truncate that sensibly, to just sort of see how many modes are important in the problem, and that gives you the upper limit for the sum. So n is the largest relevant mode number, and that's given by observation. It's different for Galerkin modes. Here modes are involved, they are physical modes, but they are only approximations to the physical modes, with resonance frequencies of an ideal tube. So if you have a non-ideal tube, these omega n's are only approximations. And yeah, the sine function here is only an approximate distribution of the modal amplitude. So this link of the individual terms in the sum corresponding to particular modes in the resonator, that link is lost, and therefore it's not so obvious what to choose for this upper limit n. In general, you have to go to rather higher numbers. I'm not quite sure what criteria there are to sort of make sure that you have got enough modes included to get decent results.
So maybe pay attention. In the Green's function, the omega n is actually the real resonance frequency of the system. Why?
Because the Green's function is a superposition of modes of your system.
Okay.
And it's the frequencies of those modes which go into the iteration.
Okay.
And in the Galerkin method, it's these idealized frequencies that go into the iteration.
Mm-hmm. Okay.
So there are only approximations. But it does work. The Galerkin method does work well. I just think the Green's function has the edge because it's physically much more direct. Okay, so this was to illustrate how to use the Green's function to calculate time histories. I now want to use it for a different purpose, and that is to analyze stability of individual modes in a nonlinear setting. So our starting point is again the integral equation for the velocity, which you have seen before, except that I've now introduced the real part. That was implicit all along, so it's a standard convention. You just ignore the real part and with the understanding that it's there. In some cases you have to sort of be careful and really take it into account explicitly, and this is one of these cases. So there's nothing new here. We now need the real part of this. We need the real part of this. And the real part can be written as, of a complex number, can be written as the complex number plus its complex conjugate, and then multiplied by a half. Right, and we can also assume that only one mode is present. So instead of taking a whole sum of modes, we'll just have mode n. And in that case, this equation becomes this. The two terms are because I've now split this real part into the actual complex number plus its complex conjugate. And I'm going to abbreviate these integrals. This is in, and this is the complex conjugate of in. So the equation for un can be very compactly written like that, where the in is given by this integral expression. Right. Now we have an integral equation for just one mode n. This equation can be converted into a differential equation, and I want to briefly outline the steps. It's rather tedious mathematics, but just to give you a flavor that what's involved. First of all, it's a four-step approach. In the first step, you determine the time derivative of this integral in that we've defined, noting that the time appears not just in the integrand but also in the integration limit, and you get this result. Then you use this result to calculate the first and second time derivative of un, which look like this. The overbars denote complex conjugate. And then you multiply, as I've indicated here. So the equation for un you multiply by omega times its complex conjugate. The equation for omega n dot you multiply by I omega. And this eliminates the complex conjugate of in and gives an expression just for the in. And then you can take the complex conjugate of that, so you have both in's, the original one and the complex conjugate. And in the last step, you take the equation for U2 dot, substitute for the i's, and simplify. So it's all a bit laborious, but straightforward. And the result that you get is really nice and simple and easy to understand. This is the result. This is the differential equation we get after doing all these manipulations of the integral equation for the velocity of mode n. As you can see on the left-hand side, we have a very well-known expression. That's the left-hand side of a damped harmonic oscillator equation: acceleration term, damping term, mass term. And on the right-hand side, we have a forcing term, which involves the heat release rate and the time derivative of the heat release rate. And it also has in there the Green's function amplitudes, the GNs, but we assume we know these, so for our purposes here, they're just constants, known constants. Right, to take this further, to take this equation further, we need to know a heat release law. We need to know how the heat release is coupled to the acoustic field. And in this example, I'm going to use a kind of an extended time lag law. So here's our time lag term. N is an amplitude, is a coefficient, and U of t minus 2, that's the time lag term. These can be amplitude dependent. So if you have a nonlinear scenario that you can describe in terms of amplitude, typically in terms of a flame describing function, then this is a good approach. And then also I've put in this term which depends on the instant time, the actual time, with another coefficient. Okay, so this is just a kind of artificial or generalized heat release law that we are going to put into our equation to see what we get, to put into the oscillator equation. So if you do that, the time lag terms appear on the right, here and here. And then this term with the n naught makes the coefficients on the left, here and here, bigger. So what we have is still an oscillator equation with a second derivative, damping term, mass term, and now on the right hand side we have these time lag terms, un of t minus 2 and its time derivative. Right, here I've written out the equation again, where the c and the b's are constants that depend on amplitude in some known way, but otherwise we treat them as constants. Right, and now we want to know, is there some steady limit cycle solution, and if yes, if so, it will probably look like that. You can describe it in terms of a limit cycle frequency. I'll call that capital omega, and that's probably approximately similar. That is probably similar to the frequency of the passive resonator of mode n. Okay, so that's what we assume for our u of t, and that allows us to calculate these time lag terms. When you deal with time lag terms, you often have to assume that the time lag is small, and then you do a Taylor expansion of these two terms. But that's very limiting because you are sort of limited to a small time lag, small compared with the period. What we are going to do here is general, so that holds for any time lag, big or small. So because our velocity has this cosine dependence, the time lag velocity has cosine of this difference, omega of t minus 2. And this cosine can be split up with the summation laws for trigonometric functions into two components, and then you can express them in terms of the velocity and the time derivative of the velocity. You can do the same thing for un dot and express that in terms of un of t and un dot of t. So that's the way to deal with the time lag terms. And if you put them into our equation up here, we get only terms with the second un derivative, the first derivative, and the original u. And again, it's a harmonic oscillator equation without any forcing now. So we can use this equation as a kind of way to examine the stability behavior, because this is a damping term. If you have a case with positive damping, we have stability. If you have a case with negative damping, we have instability. So simply by looking at the sign of this A1, of this coefficient A1, we can examine the stability behavior. And I've done this for a particular case where the case was a quarter wave resonator with a heat source near the open end, just outside, an amplitude-dependent time lag, which depended on the amplitude in this with a square law like this. So a constant plus another constant times amplitude squared. So this was how the amplitude dependence came into the time lag. And then I had a system parameter, in this case that was the tube length. And here we have the amplitude, the velocity amplitude. And I just sort of worked my way through this grid, calculating the coefficient, the damping coefficient for each point, and then marked whether it's positive or negative. And out came this stability map. So we have this region of instability. This is the red region, and all the rest, the blue, is stable. So this is the kind of result you can produce from this kind of Green's function.
Just a question. There is an advantage in comparison to using network models with flame describing functions, so it's supposed to be the same results to create this sort of map of stabilities.
I would say the advantage is that this can be done more or less analytically. Only the last bit we have to do numerically, like working out the damping coefficients, but all the rest is analytical. So the numerical effort is very, very low in this approach.
Okay.
That's the advantage. Okay, finally a summary. The analysis works well for weakly coupled cases. If you have strongly coupled modes, you can't just say, let's consider mode N, because it's coupled to another mode. So it works for weakly coupled mode. It gives straightforward stability predictions, and it's suitable for cases where the nonlinear heat release law is given in terms of amplitude-dependent coefficients, like an amplitude-dependent time lag or an amplitude-dependent coupling coefficient, whatever. And I think that's the end. Yes, thank you. Questions?
So the time lag heat release law. So this is something that we observe experimentally.
Yes, there has been done. The work has been done at École Centrale in the Candel group. A chap called Nicolas Nouré did a PhD. He actually measured the flame describing function for this quarter wave resonator.
And that gives you this N1 and N0.
Yes. So yeah, he found. Well, he measured the flame describing function, and from these results, I sort of reconstructed the heat release law, and I found that it has both an independent, an amplitude-dependent time lag.
And any chance of linking it to physics, to N1 and N0, or is it difficult?
I have some ideas, but they're not easy to explain. The physics, I mean, what's the physics? What physical effects limit the amplitude or have an effect on the time lag? If your flame at high amplitudes, your flame becomes longer. I mean, it has to stretch more. So for a disturbance to travel from the base of the flame to the top, it takes longer. So that would explain why the time lag increases with amplitude.
Yeah, question. At the beginning of the analysis, you start with the Green's functions and you neglect. You just take one mode and you put all the other modes aside.
Yes.
Yeah.
Yeah.
I think have you also made computations with all the modes included?
This is current work. This is Alessandra's topic. Unfortunately she's not here, but yes, we are working on an extension.
I think it's very interesting to really capture nonlinearities and mode conversions and so on.
Yes.
Okay.
This is ongoing work.
Okay.
Yes? This thing that you just mentioned, that for higher amplitudes and longer flame it takes longer time, is it not in contrast with compactness of the system? Or we don't think about compactness when we...
Compactness means the flame is short compared with the wavelength. Okay? So I'm not talking about the flame becoming 10 times longer, just a bit longer. It's still compact, it's still short compared with the wavelength.
So the order of like this time lag differences we're talking about in flame describing function is quite small?
Yeah, it's if for zero amplitude is, I don't know, say a quarter of a period, then it may be twice that. at the sort of maximum amplitude that can be measured. So it doesn't change that much, maybe by a factor of 2 in the sort of largish amplitude range, but not by a factor of 10 or 100. It's a fairly moderate change, but it's big enough to have an effect on the stability behavior.